class I am going to explain you about integrated circuits. So integrated circuits are made up of several components such as resistors, capacitors and inductors, diodes and transistors. So you can see the images of the components that have been used in integrated circuit. So that's why the name integrated we can call it. So they are built on a small single block or chip of a semiconductor known as an integrated circuit. So all of them work together to perform a particular task or work. So you can see it is built on small single block of a semiconductor chip. So if we come across resistors, capacitors or inductors or other electronic devices or components. Two types of integrated circuits are there. So analog integrated circuit and digital integrated circuit. So analog is a continuous wave. So you can see here this is like sine wave, and digital integrated circuit, it is a square wave. So analog integrated circuits are integrated circuits that make a representation of continuous signals in electrical form. So it is continuous, the waveform, the output of the analog circuits are going to be continuous signal. So some of the examples are memory chips, power supply chips and sensors, wideband rectifiers, and especially good example is operational amplifiers. So in this class we are going to study especially about operational amplifiers. So digital integrated circuit, as the name indicates, it is going to be numbers, either it may be 0 or 1, like high or low values. So that's why the output looks like a square wave, either it may have a low value or high value. So a digital integrated circuit is an electronic device that collects several digital electronic components on a small semiconductor chip. So usually each integrated circuit is designed to perform the particular task. So some of the good examples for digital integrated circuits are timers, logic gates, calculators, counters and microprocessors. So as I said, in this class we are specially concentrating on operational amplifiers, which are a good example for analog integrated circuits. So first we should understand what is the operational amplifier definition. So an operational amplifier is a DC coupled, direct coupled, high gain electronic voltage amplifier with a differential input and usually a single ended output. So it has a high gain electronic voltage and differential input and also single ended output. So the symbol of the operational amplifier, it is having the two inputs, that is non-inverting terminal and inverting terminal and output terminal. So we can have IC741 example. So here along with this we will come across positive and negative power supplies here. So this is the symbol of operational amplifier. So some of the important characteristics of ideal operational amplifier are: first one, infinite open loop gain. Okay, gain is infinite input impedance, so zero input current, and zero input offset voltage, input output voltage range, the bandwidth with zero phase shift, and infinite slew rate, and zero output impedance, infinite common mode rejection ratio, infinite power supply rejection ratio. So these are some of the important characteristics of ideal operational amplifier. So the applications of operational amplifier, it may be used as linear, non-linear, or in the wave shaping. So here linear devices like adder, subtractor, and integrator, differentiators, log and anti-log amplifiers. So non-linear are comparators. Okay, then Smith trigger, clippers, clamper, and oscillators also we will come across. So wave shaping, sine wave generator, triangle, rectangular wave generators, so multi vibrators. So some of the applications of operational amplifiers we have here. So the first comes here, inverting operational amplifier. So as we know, there are two inputs, inverting and non-inverting terminal. So the inverting operational amplifier, it is amplifier using an op-amp, is a type of amplifier where the output waveform will be phase opposite to the input waveform. So negative and positive signs has been given. Input terminals. So negative sign indicates inverting operational amplifier. Whenever the input we apply to the inverting terminal, output is going to be opposite of its sign. So the output of the inverting operational amplifier is given by, or gain we can call output by input, that is gain is equal to, the gain is going to be negative here, ratio of feedback resistance to the input resistance. So feedback resistance is connected across the inverting terminal and output terminal. So the next comes non-inverting operational amplifier. So the non-inverting operational amplifier produces an output signal that is in phase with the input signal. Whatever the input we will provide, like sine wave, if we provide, output is going to be sine wave. In case of non-inverting, inverting, if we provide input sine wave, output is going to be square wave. So input, whatever we provide here, the same output we are going to get. So the gain is going to be 1 plus, so feedback resistance to the input resistance, R2 by R1. So this is the gain of a non-inverting operational amplifier. So the next comes summing or adder amplifier. As the name indicates, we can understand the definition of each different types of amplifiers. So the summing amplifier produces a voltage output that is equivalent to an applied sum of two or more input voltages. Whatever the inputs we are providing here to the inverting terminal, the output is going to be the sum of some or more input voltages, that is equal to V1 plus V2 plus V3 like this. But the output is going to be negative because we are going to apply here inputs to the inverting terminal. So the subtractor here, an op-amp based subtractor produces an output equal to the difference of the input voltages applied at its inverting and non-inverting terminals. Whatever the inputs we are going to apply across two input terminals, 2 and 3. If we take IC 741, 2 and 3 are the inputs, so 6 is going to be output. 7 and 4 where we apply DC power supply. So whatever the input we apply across inverting and non-inverting terminal, the difference of the two inputs is given by the output of the op-amp. So that is here output is equal to the ratio of feedback resistance R2 divided by input resistance R1 into V2 minus V1. So integrator, in an integrating circuit, the output is the integration of the input voltage with respect to time. And one more thing here, integrator operational amplifier, we are going to use capacitor instead of resistance, feedback resistance. So in the feedback circuit, we are going to use here capacitor. So here output is what? Integral of the input voltage, that is equal to minus 1 divided by R into C, resistance into capacitance, integral of input voltage with respect to time. So differentiator, it is quite opposite to the integrator. So here we are going to apply capacitor in the inverting input terminal. So here feedback circuit is connected with resistance. Here output of the differentiator is proportional to the rate of change of input voltage by measuring the current through the capacitor. So we can have the formula here. Output voltage is equal to minus resistance into capacitor rate of change of input voltage, V input divided by dt. So logarithmic amplifier, the log amplifier gives an output voltage which is proportional to the logarithmic of the applied input voltage. So here in this circuit we can see the feedback circuit is going to be replaced with diode. In case of integrated differentiator we are going to use capacitor. In case of logarithmic and as well as exponential circuit we are going to use diode instead of feedback resistance. So here the output is what logarithmic of the log of the input voltage or input current we can write. Output voltage is equal to V in log of feedback current to the input current. So the next that is exponential amplifier. It is exact opposite to the log amplifier. So anti-logarithmic or exponential amplifier we can call. So here the output is proportional to the exponential value of anti-log value of the input. So here the equation for the output voltage for exponential circuit. So here the diode is connected across inverting terminal. So output is equal to minus I naught RF exponential of input voltage to the eta into V tau. So these are the different applications of operational amplifier. We can use operational amplifier as a exponential, logarithmic, differentiator, integrator or subtractor, summing or adder amplifier, inverting, non-inverting operational amplifiers. So this is all about analog integrated circuits. So I hope this information is helpful for you.